Welcome back. Today, let's begin chapter number 5. We have a total of 6 chapters. Chapter number 5, which is on charge flux. So far, we had seen mass flux. Of course, initially we saw some mass conservation, then mass flux, momentum flux, thermal energy flux or energy flux with a focus on thermal energy flux, and now charge flux. Why do we need to look at charge flux? Okay, after all, not many engineers look at charge flux. Electrical engineers do, but not many others look at charge flux as a fundamental aspect. Okay, but we need to. Why? Because the fundamental biomolecules that make up all biological systems are these. You recall this from your biochemistry course: lipids, carbohydrates, proteins, and nucleic acids. Okay, these are the 4 kinds of biomolecules, the fundamental biomolecules that make up all life. Lipids are charged. You recall your cell membrane, your bilayer lipids, or other lipids, they are charged. Carbohydrates, many are charged. Okay, not all are charged. Glucose is not charged, but many are charged. Okay, especially the surface carbohydrates and so on and so forth, they are charged. Proteins, they are charged. Proteins are polymers of amino acids. Have an amino group, a carboxy group, a peptide bond in between the amino acids that makes the protein, and you could have charged groups on as the R groups and so on and so forth. So proteins are always charged. Their charge depends on pH and so on and so forth, yes, but they are predominantly charged. Nucleic acids, of course, charged, right? Remember the structure of a nucleic acid: sugar, pentose sugar, nitrogenous base, and a phosphate group. Depending on the type of sugar, either a ribose sugar or a deoxyribose sugar, you had either a RNA or a DNA, and you have phosphate group there, you have the nitrogenous base there, full of charges. Okay, so these are charged. So your fundamental biomolecules are charged. Therefore, biological systems are charged. Therefore, not just that, charges and their dynamics are responsible for our ability to sense our environment through our various senses: sight, smell, taste, touch, and hearing. Okay, we'll see some of this in the next chapter, the basis of this in the next chapter. The dynamics of charges are essential for the functioning of our nervous system, our brain, our heart, and so on. Okay, so it starts affecting at the base level, very fundamental level. So charge is a fundamental physical quantity, and also charge is a fundamental physical quantity that is conserved. Okay, so a better understanding of the fundamental relationships related to electrical charges and consequent or parallel aspect magnetism, the better understanding is expected to significantly equip the manipulator of biology. And that's the reason why even undergraduates need to be comfortable with charge flux aspects in biological systems. That's an essential aspect to understand to effectively manipulate biological systems. So let's start with some of the formulations that are centuries old in electricity. Okay, electromagnetic theory, electromagnetic aspects, and so on. So some fundamental visualizations which have existed for centuries is that the space between interacting charges can be considered to be influenced by the charges. This was what was mentioned by Faraday. Okay, and recall what we talked about when Faraday was researching into this. One of the politicians of that time came and asked him, what's the point in doing some white elephant kind of work, okay, ivory tower kind of work. Okay. Imagine electricity being called an ivory tower. You have pretty much nothing today that you cannot think of a life without electricity nowadays. So that's what happens. You should not neglect the fundamental aspects. They would have a long significance over a very long term. So you need to give it due respect and due care and so on. So the forces between two charges, let's say two charges, are transferred from one charge to the other through the space in which they are located. This is the picture which helps understand electrical aspects and magnetism aspects. Okay, the force between, say, two charges are transferred from one charge to the other through the space in which they are located. Therefore, electric and magnetic fields, the region of influence, exist at a point in space even in the absence of actual charges at that particular point. Okay, this is worthwhile understanding in great detail. Electric and magnetic fields are nothing but the space where there is influence. Fields exist at a point in space even in the absence of actual charges at that particular point. Okay. This is a fundamental view of charge. Now, let us consider the effect of those fields on a charged particle and the force experienced by that particle. So, you have a field, you have a charged particle, we are looking at the force that is experienced by the particle. Okay. Can you recall what's the force that is experienced by the particle? You have already seen this. I'm sure you would have seen this as a part of your physics course at higher secondary school level or at the first year level of your engineering curriculum. Okay. Can you recall what that is? What's the effect, the force experienced by a charged particle when it is in the presence of an electromagnetic field? Pause, go back, check, and so on if you need. That is given by the Lorentz force law. Okay, the force experienced by a charged particle in an electromagnetic field. It is something like this. We need to understand this clearly. Therefore, let us review certain things that you know already. Maybe you don't know it in this level of clarity and so on, but a high clarity is needed for us to understand these electrical aspects also. The force F experienced by a test charge Q that moves at the velocity v in such a field is given by the Lorentz force law. You know this. The force experienced by a test charge that moves with a certain velocity in an electromagnetic field is given by F equals Q times E plus V cross mu naught H. Okay. Recall the Lorentz force law. Equation 5.1-1, where E is the electric field density, H is the magnetic field intensity, mu naught H is the magnetic field density. These are the terms. By the way, in electrical engineering, the terms would be slightly different, especially if flux is used in a slightly different context. Don't get confused between that and this. I have taken enough care to distinguish between those, but just keep in your mind that when you see flux from a point of view of electrical aspects, you need to make sure what you're talking about, okay? Because the historical development has given a slightly different meaning to flux than what we understand flux as in this course, okay? Of course, metabolic flux is nothing but metabolic flux was nothing but a metabolic rate. In this case, they mean something else, and so on and so forth. We cannot erase history. We cannot erase how they have been used for a long time. So we just need to get used to that without confusing our usage with this usage. Mu naught, of course, is the permeability of free space. The value is 4 pi into 10 power minus 7 Henry per meter. These are the units. This is some sort of a review for you. So go back and check your high school first year notes to understand these better, or textbooks. Henry is volt second per amp. Okay. Now, if the electric field is E, the electrical force on the charged particle with a charge Q, test charge Q, is QE. Okay, it will be in the same direction as that of the electric field. If the magnetic field density is mu naught h, or magnetic field intensity is h, if we consider the plane of the velocity and h to be something like this, okay, then the magnetic force would be in the direction that is perpendicular to the plane that contains v and h. Okay, there is a certain velocity, there is a certain magnetic field intensity. You can form a plane with those, and the magnetic force is going to be perpendicular to that plane. That is what is indicated here. Q times v cross mu naught h, both these are vectors, is in a direction. The cross product would automatically give you this as the direction of the force. So you have the electrical force here, you have the magnetic force here, and therefore the total will be in this plane that contains QE and the magnetic force QV cross mu naught h. These two, if you consider as a plane, the resultant force is going to be this way. So a vectorial sum of QE and QV cross mu naught h would be the resultant electromagnetic force on a charge q moving at a velocity v. Remember this. I hope you got the directions fine. If not, you go back and revisit this. Let me very briefly mention again what we said. This is the electric field E. The electric force will be in the same direction as the electric field E. The magnitude of that will be Q times E. The magnetic field would be in a direction that is perpendicular to the plane that contains the velocity and the magnetic field intensity. The value of the magnetic force would be Q times V cross mu naught H. And what we are interested in is the resultant force of the electric force and the magnetic force. So if we consider the plane that contains the electric force and the magnetic force, you can always do that. These are two vectors. You can construct a plane there. In that plane, you will find the resultant force. And of course, you can find out the vector sum of these two. That would be the direction and magnitude of the resultant electromagnetic force. Okay. We need to get a review or get used to some terms: charge density and charge flux. Charge density is quite straightforward. Let us consider a small volume, delta V. Okay, again, neighborhood concept, small enough for something, large enough for something else. So let us consider a small volume, delta V, with a net charge within it. We always look at net charge, by the way. Okay, everything relates to net charge, which is sum of positive and negative charges put together. So the charge density rho is defined as the net charge in delta V divided by the volume of that small volume element, if you want to call it so. So the charge density is net charge in delta V divided by delta V, coulomb per meter cubed. Equation 5.2-1. This is charge density, quite straightforward, quite intuitive. Charge flux again, okay, before that, let me re-emphasize that delta V is chosen to be small enough compared to system dimensions, but large enough to contain many charges to ensure continuum conditions. Okay, some sort of a neighborhood concept that we saw when we looked at turbulent flow and so on and so forth also. So, or species concept. Okay, this is very similar to the species concept in the volume, much smaller compared to system dimensions, but large enough to contain many unitary aspects, in this case charges, to ensure continuum conditions. If a charge density rho moves with the velocity v, the charge flux I dash. Okay. Note I am calling this I dash as charge flux because I is reserved traditionally for a different quantity. We will see that later. So charge density rho moves with the velocity v, charge flux I dash is rho times v. Okay. Work out the units: coulomb per meter squared per second, coulomb per second per meter squared. Okay. Amount, in this case coulombs, is the amount of charge per time per second per unit area perpendicular to the direction of transfer. So, charge flux I dash. Equation 5.2-2. We are more familiar with the term current, and current is nothing but charge transport, and is a measure of rate of charge with time. Okay, there is no area aspect here, and we are going to retain the symbol I for that, and that way we will be in line with the traditional use of I. So, I am going to call this as I dash. By the way, the development here you won't find in any book except mine, and also some of the development you won't find, especially the derivation of the charge conservation equation you will not find. And also the derivation that I am going to give you here is different from the one that is there in the book. Note that the book was written 10 years ago. Okay. Subsequently, I have been teaching this course ever since, and even before that. And I have found more direct ways of telling you things without confusing students. Okay, so I have brought in that entire experience into this course. So whatever you're getting is years of experience, so that you will find it much easier to follow. Okay, now the charge conservation equation. This is what I meant. This is not there in either any book or my book. This is a part of this course for the outside world. I've been teaching it this way for many years now. Once I realized that you could do the same conservation aspects as we did for mass, momentum and energy and come up with the same equation. Okay, now let us derive the charge conservation equation. We have derived the mass conservation equation, we have derived the momentum conservation equation, then the energy conservation equation, now the charge conservation equation. Let us consider the intuitive Cartesian coordinate system that we have considered earlier. Let us say that the charges are moving through this control volume in 3 dimensions. So, the same thing, x, y, x cross y equals z. This is x, y, z, this is x plus delta x, y plus delta y, z plus delta z, and charges are moving in all 3 directions. The total charge conservation is similar to total mass conservation, input minus output, because charge can neither be created nor destroyed. Okay. So, we are looking at total charge, okay, no negative, no positive separately, total charge. So, dou C is charge, dou T equals Ri minus Ro. Total charge is conserved, and therefore, there is no generation or consumption term in this balance. Let rho be the net charge density. This you should internalize. It's net charge density. Let I dash be the net charge flux, amount transferred per unit time per unit area perpendicular to the direction of transfer. And the net charge balance equation just becomes accumulation equals input minus output, as we have already seen right here. This is input minus output. So, the net charge can be written as net charge density times the volume, right. So, dou T of rho delta x, delta y, delta z is going to be this, and input is through the phase at x, through the phase at y, through the phase at z. Output is through the phase at x plus delta x, y plus delta y, and z plus delta z. The flux, the charge flux is Ix, the x direction charge flux is Ix dash at x through the phase at x times the area, that is what this means. This is the y flux through the phase at y times the area delta x delta z. This is the z flux through the phase at z delta x delta y, area of that phase, minus the output terms. Okay. So, this is quite straightforward. Now, if you divide throughout by delta x, delta y, delta z, the usual things, and take the limits as delta x tends to 0, delta y tends to 0, and delta z tends to 0, then we get dou rho dou t equals, these are nothing but the negative of the definition of the derivatives. So, dou x of ix dash plus dou y of iy dash plus dou z of iz dash. This is nothing but del dot I dash, and that is what is given here. So, dou rho dou t plus del dot I dash equals 0 is the charge conservation equation. Simple derivation. Okay. So, this is something that I had developed with inputs from one of my students who was bright. Okay. Debayan. Yeah. He had provided the initial things. He had tried to write it in a different way, and based on that, I had developed this. I had asked him to develop that because he could see things clearly, and then he wrote it in a different way because he had considered negatives and positives separately, and so on and so forth. We need to look at net charges, and this comes out in a very small number of steps. Okay, I think we need to stop here. There are a lot more basics that we need to become comfortable with. So partly review, partly new kind of a mode we are going to be in the next class also. See you in the next class.